General relativity, step by step. I've got this nice trial metric here, and what I want to do now is to try and pin down a of t and q of r, these two functions here, which appear in my trial metric, using physics. So that effectively means that I've got to solve the Einstein field equations, which I'm going to write down now just to remind ourselves what we're doing. So let me pinch in a little bit. We've got the Ricci tensor mu nu minus a half r for the Ricci scalar g mu nu plus cosmological constant, and that equals the right hand side, which is my field 8 pi g over c to the 4 t stress energy tensor mu nu. So what I want to do is to solve this equation, and hopefully that'll give me some differential equations, or some information at least, about a of t and q of r. Incidentally, you quite often see a of t, which the concept I've written down a of t, you just quite often see it written down as a, but I don't like that because it obscures the functional relationship, because I'm assuming that a is only a function of t, it's not a function of r. And similarly you'll see q, which is really a shorthand for q of r. Sometimes I might use this notation, but it's important to remember what's going on. Okay, so the first step to solving the Einstein field equations is to evaluate the Ricci tensor, and to do that I need the Riemann tensor, and to do that I need the Christoffel symbols. And to evaluate the Christoffel symbols I need the metric tensor. So what I'm going to do is to write down the components of the metric tensor in this particular coordinate system here. Actually, I'm going to need more space than that. It's going to, let me just put it down here, go up a little bit, down here. T, R, theta and phi, T, R, theta and phi, minus 1, 0, 0, 0, 0, and what was this term here? That was just a of t squared. A of t squared, 0, 0, 0, 0, a of t squared, q of r squared, 0, 0, 0, and what was this one? That's a of t squared, q of r squared, sine squared theta. Okay, so that's my metric with downstairs indices. Now, it's easy to go from that to the metric with upstairs indices because I just need to take a reciprocal of these terms here, because the matrix inverse of a diagonal matrix is just the diagonal matrix of the inverse of the diagonal of the first matrix. So that's quite easy. Right, so what I'm going to do now is to use that. I'm going to pinch in a little bit, but I don't like doing that because it makes my writing quite bad. We've got Christoffel symbols, I'll say alpha, beta, gamma, and we've got, of course, 4 times 4 times 4. We've got 1, 2, 3 factors of 4 there, because we've got 3 indices, and it's a half of that because we are assuming symmetry in the lower 2 indices, which corresponds to 32. What I'm going to do is to evaluate 1, just to say how it works, and then I'm going to use a computer algebra system. So, the one I've chosen to evaluate is this one, gamma T R R. That's the Christoffel symbol for T, R and R. So the way to evaluate it is to get rid of that for a start, because I need to keep my it zoomed in as much as I can. So it's going to be alpha, beta, gamma equals 1/2 G with upstairs indices alpha delta times di G and then downstairs di x below plus di G do by di x d minus di G da da by di x da. Now I need to fill in the gaps. The delta is the summation variable which sums on the first place, the second place and the downstairs place. We've got beta and gamma left over. It must go there and then there. Oh no, got it wrong. The beta should be on the denominator, G, and that should be a beta, and that's a gamma, and then beta and gamma are together here in the term with the odd sign summed over the denominator. And in this case, because the term we are evaluating is this one here, TRR, we know, pinch in a little bit here, we know that alpha equals t. We know that beta and gamma are both r. Beta equals gamma equals r. But we also know that delta equals t as well. Because we're summing over delta, but the only non-zero term in our metric tensor is this one here, so we can ignore the other terms, they're all zero, because we've got a beautiful diagonal metric tensor here. So that means I can just write out the terms. That's going to be a half g. I've found, incidentally, that it's good to do the Christoffel symbols in 2 stages or even 3 stages. What you do is you write out the definition and then you write down what the various indices mean, then you do the substitution, then simplification, and then right at the end you substitute for the particular tensor that you've got. Okay, so we've got alpha and delta are both t, so that's g superscript tt times di g and then delta beta. That's t and beta is equal to r by x gamma, which is di r. Well, yes. Well, you see, I can tell that that's 0 because this is an off-diagonal term. So I can cancel that one away straight away. I don't need to worry about this one. That's equal to 0 because from here we are looking at g subscript tr, which is this term, or this one here, I guess, which is just 0. Back to black. Plus di g, and then gamma equals r and delta equals t by, it doesn't matter because this again is an off diagonal element on my matrix here, which is this one here. It doesn't matter, so I can use my red pen and cancel that out to 0. That's great. Back to black. Minus di g t, oh no, it's not t. That beta there, this beta here is an r, and that gamma there is an r. So it's grr by di x, by di t, I guess, because its x delta is t. Equals 1/2 g superscript tt times, oh, it's a minus sign there, it's easy to forget, minus di by di t of g subscript rr equals, well, now we can do our substitution here. From the metric tensor, which I've got written down here, it's minus 1/2 times g subscript tt, sorry, that's a superscript tt, so it's 1 over, well, I may as well write it in, 1 over minus 1, because it's the reciprocal of this term here, because this is g with downstairs indices, and here we need upstairs indices, times di by di t of g rr with downstairs indices, which is just a of t squared. A of t squared. I'll put that in brackets. Yes, this is looking nice. So that's plus 1/2 of di by di t of a of t squared, which is just a di t, a of t. I guess you could write it down a little bit more simply than that. It's just a dot. There it is. Brilliant. So we've got one of our Christoffel symbols. So we know that the Christoffel symbol TRR, which I've been working on, is just a dot. Fantastic. Stop there. Stop, 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 stop.